Okay, all right. It has started recording, so let's start. So last time we started chapter 3 of Lang and discussed the notion of dual lattice. And today we will continue. We will introduce what is called the different ideal. Uh, it's an important concept, and it is related to it's a very useful thing to study a ramification of primes. So let me start sharing the screen. Yeah. Okay. Uh, Okay, one of you could confirm that you can see.
Yes, sir.
Okay, so today we are going to discuss this notion of different, very important concept, and we will see. Okay, so last time we started chapter 3 and discussed the notion of a dual lattice. So for you have an extension E over K, finite separable, and you have K is the quotient field of A. You are taking B to be the integral closure in E, and if you have any additive subgroup of E, we introduce this notion of what Lang calls complementary module or dual lattice. Okay, and so we saw that the dual of a lattice is a lattice. This we did using, this was easy, using the dual basis, fix an integral basis and take a dual basis with respect to the trace bilinear form. And we saw that the dual of a fractional ideal is a fractional ideal. And we also saw that we computed an explicit dual basis. So what is the natural base of k alpha over k? 1 alpha, alpha square, etc. And then we constructed a dual basis. This depended on the minimal polynomial of f and its coefficients. And then we proved that for an extension of dVRs with only one prime lying above B, above B, then B is of the form A bracket alpha. Right? This if you recall in chapter 1 itself, using Nakayama, we have shown that B is A generated by two elements, beta and pi we called it, where one of them, beta, is a generator of the residue field extension, which we are assuming is separable, and a lift of that. So take a generator of the residue field extension, take a lift, and then also take an order one element, evaluation one element pi, and then these two will generate. And using this, we showed that using some calculation, using valuation, we showed it's of the form A bracket alpha. So in particular, for in the local situation, if you assume that the field is complete, all these things are true. There's exact, the ring of integers is a DVR, and there's exactly one prime lying above, so this can be applied. This involved Nakayama and an argument using valuation. And today we are going to introduce the different ideal of B and look at its properties vis-a-vis ramification. Okay, so that's what we will do today. So recall dual lattice. You have E containing K separable, B containing A. K is the quotient field of A, and B is the integral closure of A in E. And this is how we define. So if L is an additive subgroup of E, then L prime was defined as all those X such that the trace of XL is contained in A. And L equal to B is an important special case. Important in what sense? We had extra observations we had made in this case. If B turns out to be A bracket alpha generated by one element as a ring, then we determined B prime is B by F prime alpha. F is the minimal polynomial of alpha, and then it is generated by 1 by F prime alpha. Okay. And also we saw that maybe I left it as an exercise that B prime controls the dual of any fractional ideal. In what sense? If you have a fractional ideal script B, then its dual B prime is nothing but B inverse multiplied with B prime. So small b prime is capital B prime times B inverse. So these properties we have seen. So now let's continue. So you have transitivity. You have the notion of transitivity. So what happens is, suppose you have an extension of extension, separable extensions E over F over K, and K is the quotient field of A, and consider the integral closure of A in F, call it C, and the integral closure of A in E, call it B, and you have thus the respective integral closures. Now you can ask how the dual lattices will behave. So suppose B prime is the dual lattice of B with respect to E over K, meaning the definition of B prime is all those x in E such that trace from E to K of xb is contained in A. Right? Your definition had trace contained in A, and trace is taken with respect to E over K. Here it is x in E such that the trace of xb is contained in F, traces from E to F. And this is all those x in F such that trace from F to K, xc is contained in A. Okay, so you have these three. So given such an extension of extensions, you have three dual lattices and they are related nicely. So E over K is E over F times F over K. So what is the interpretation of all these things? What is this? This is a fractional ideal, right? This is a fractional ideal of B, and this is a fractional ideal of B, and this is a fractional ideal of C, but C is contained in B. So this product makes sense. Okay, so these are all fractional ideals of B or of C, and the product makes sense. So let's prove this first. This is easy. So this is the first direction. If you take, so you have to show that this is contained in this and this is contained in this. So let's take an element of this. We are going to show that the RHS is contained in LHS. Take an element of this. Take an element from this and multiply by B and traces from E to K. Okay, so if trace from E to K of xb is contained in A, then x belongs to this. Then x belongs to the dual lattice of E over K. So that's what we are going to show. We are going to show that this is contained in A, and that will show that this set is contained in B prime E over K. That will be one direction. And why is this? This is because trace is transitive, nothing more. So trace is transitive. So you can write it as E to F followed by F to K. Inside is the same thing. Now remember, what is C prime? C prime consists of elements from F, but this is trace from E to F, so that can be pulled out. So this C prime can be pulled out and the remaining is as it is. But now trace B prime E to F, by definition this is contained in A. This is contained in A by the definition of B prime E over F. Therefore, this is contained in trace of C prime A, but that is contained in A because by definition trace F to K of this will be contained in C, but C is contained in A. So this is okay. So C is contained in, as A is contained in C. Oh, okay. So maybe I made a mistake. So by definition, what is this? C prime consists of those elements X and F such that trace of this consists of those elements X such that trace of XC is contained in A. Trace of XC is contained in A. So if you have an element here, correct, yeah. So as A is contained in C is fine because if you have an element here, then trace of xc is contained in A. So if you take anything from C here, then this product trace is contained in A. So A is contained in C. So if you take an element in A, then in particular it's in C, and therefore this is contained in A. So that's okay. Okay. Therefore, what you have shown is this product is contained in B prime E over K. Now, what about the other direction? For the other direction, suppose X belongs to B prime E over K. Now you have to show that X belongs here in this product. So suppose X belongs to B prime E over K. Then by definition, trace of XB, E to K trace of XB, this is contained in A. That's the definition. But what is trace of XB? Trace of XB is by transitivity of trace E to F and F to K. And this trace of E to F of XB, you can insert a right. So if anything is in C, then that comes out because C is contained in F. So now what you can do is, instead of B, you can write it as CB because product of C and B is B only because C is contained in B. So what you do is you write B as CB and then C comes out. So what you have is trace of E to F of XB and C comes out. Okay. Because B is CB, you insert and do this operation. Now what do you observe? Now trace from F to K. Yeah, you know that this is contained in A. You know that this is contained in A. So this is contained in A. So trace from F to K of something times C is contained in A, then that something belongs to C prime E over F. So C prime F over K. So trace of XB is contained in C prime F over K. In other words, C prime F over K inverse times trace of XB that is contained in C. Right? This is the fractional ideal of C. So if you multiply by its inverse, then that is contained in C. But C prime F over K inverse, this by definition is contained in F. This is contained in F, and therefore you can put that inside. This goes inside. So trace of X times C prime inverse B is contained in C. Just by putting this back, taking this inside the trace, so you get this. What is your aim? You want to show that X in B prime E over K. You want to show that X is contained in that product. B prime E over F, C prime F over K. Okay. So so from this, what can you conclude? This is trace from E to F of something times B is contained in C. So that means this product is contained in B prime E over F by the definition. All, these are all simple things. I'm just using the definition in various ways. So this is contained in B prime E over F. So this is contained in B prime E over F, then X is contained in B prime E over F times C prime F over K. So that's what we wanted to show. We wanted to show that this dual lattice is transitive and both sides just the definition, nothing more. Okay. So now we are going to introduce the definition of different. It's going to be an ideal. Okay. So for E over K, we are going to define an ideal of B, which contains a lot of information about the ramification properties of properties over B over A, of B over A. So it's called the different and defined as, this is a notation, dB over A, the different of B over A. It's an ideal of B, it's an ideal inside B. And the definition is, we have introduced the notion of dual lattice for E over K and take its inverse. Can you tell me whether the dual lattice contains the element 1? Check the definition of dual lattice. Does this contain 1? Where L is B. If B prime, does B prime contain 1?
Yes.
Yeah, because trace of XB is contained in A, X is 1, so trace of B is contained in A is true. So B prime contains 1 and therefore B prime contains 1 and therefore what can you say about its inverse? This contains 1. So you have a fractional ideal with containing 1. So fractional ideal containing the ring and then you are taking its inverse. So what can you say about a fractional inverse of a fractional ideal which is bigger than the ring? Inverse of a fractional ideal is a fractional ideal. And because this is originalist bigger than the ring, the inverse will be contained in the ring. So it's a fractional ideal contained inside the ring. In other words, it's a genuine ideal. It's an integral ideal. So it's an ideal since one belongs to this. So different you have defined as the inverse of this particular dual lattice of the ring, of the unit ring. And it's an ideal, and this is called the different. And we have already proved this thing. What is the proof? Why is this true? And claiming that different has this property. The ideal different is transitive. Why?
We just saw the transitivity, no?
Because we just for the inverse we showed the transitivity. So on that transitive relation for dual lattice, you take inverse everywhere. So you get transitivity here. Okay. So observe that the different behaves well with respect to localization. What I mean is, if you have B over A and if you have a multiplicative set S in A, then you can consider S inverse B over S inverse A, and you can take the different there. And the answer is, it is nothing but the localization of the different. So different of the localization is localization of the different. You check this, it's very easy. Just follows from the definition of localization. S is a multiplicative subset of A. So again, once again, you check for dual lattice how it behaves with respect to localization. And just apply the definition of dual lattice, you will get this. Okay, so check this. So this is the first part. Different behaves well with respect to localization. And we are going to show that it behaves well with respect to completion also. So Q to QP, right? From Q we had periodic numbers. So fix a prime ideal. With respect to that, you have an absolute value. In that absolute value, you complete. With respect to that metric, absolute value gives you a metric. So that metric space you complete. And with respect to that operation also different behaves well. So it can be computed purely locally. So to do this, you may assume that A is a DVR. Why can you assume A is a DVR? Because of this last thing that I asked you to check. Different doesn't change. Different of the localization is localization of the different. So A is Dedekind. So localizing at a prime, you will get a DVR. And it's enough to do this for a DVR because it behaves well with respect to localization. So you can assume it's a DVR. This is because different behaves well with respect to localization. So you can assume that A is a DVR and it has a unique non-zero prime P. Unique non-zero prime P, and it has a corresponding valuation VP. So how is valuation defined? So if you take, it's a DVR, so P has a generator pi, and any element is of the form pi power R times a unit, and the valuation of that element is the power of that irreducible element pi. So valuation of pi power R U is R. That defines a valuation that gives you an absolute value. Mod X is 1 by norm of P, C power minus R, but the good choice of C is 1 by norm of P, norm of the ideal P. Okay. So as usual, the quotient field is K, E over K finite separable. B is the integral closure of A in E, and let P be a prime lying above P, and corresponding valuation you can denote by WP, right? Anytime you have a prime, you get corresponding valuation, and then you can complete. So A completed with respect to V is AV, and B you can complete. Yeah, so what do I mean by completion, respective completion? What I mean is you have a valuation on K, you complete K, and in that you take the closure of A. Okay, so you have A is contained in K is now completed. So typical example is you have Z, you have Q, take a prime number. At that prime number, if you complete, you get QP, periodic numbers, and you take the closure of Z. In that metric, you take the closure of Z in QP, and that is ZP. So that's a completion. Okay, that's what we mean by completion. So you have AV and BWP, the respective completions, and then the result is you can take the difference of B over A and see how multiply it with this local ring, this completion BWB, and that is nothing but the difference of the local rings, different of the completed rings. So sometimes we call this the global difference. This is global in nature, global difference. This is after completion, so that is called local. Okay, more like chapter 2. This is more like chapter 1 and this is more like chapter 2 of Lang. But these two are nicely related. The global difference multiplied by the local ring is the local difference. Okay, so this requires a proof which we will skip for the time being. So right now let's skip. If we have time remaining, which I doubt because we want to do other things. So some you can read if you are interested. You can read. The proof is there in Lang. It's not very difficult. Okay, so the conclusion from this slide is you have the notion of a difference. You can complete and move to the local situation, and locally you have the different, globally you have the different, and they are connected very well. The global different times the local ring is the local difference. And earlier, from whatever we have done earlier regarding ramification, also ramification also behaves well with completion. So both this different and ramification, they behave well with respect to completion, also with respect to localization. We have seen long back that ramification indices they do not depend on they do not change after localization, and similarly they do not change after completion. So here is a statement. It's easy to prove. I will leave it. So let A be Dedekind, P be a prime, corresponding valuation is V, and K is the quotient field of A, and KV is its completion with respect to this absolute value. And then you take the closure of A in KV, call it AV, and PV is the closure of P in AV. You can check that AV is a DVR and PV is the unique prime ideal, and if A is any fractional ideal, then it can be written as a power of, there's a unique prime ideal, so it will be PV power RP, where RP is an integer. If A is an ideal, it's positive. If A is a genuine fractional ideal, then it's negative. Okay, but what you should observe is, what is this RP? This RP is nothing but, this RP is purely already understood. So A you can write in terms of, so A you can write what is A? A is a Dedekind ring, right? So A you can factorize. What do you mean by A you can factorize? A is a fractional ideal. So by after multiplying by an element, it's an ideal. That ideal you can factorize. So the factorization of A will be the factorization of that ideal divided by the factorization of that element, meaning the principal ideal generated by that element. So any fractional ideal you can write as a quotient of product of prime ideals. Product of prime ideal divided by product of prime ideals. So A you can write as product of prime ideals by product of prime ideals. In other words, you can write it as a finite product of prime ideals where each prime is coming with a power which could be positive or negative or zero. Or zero, I don't need to say, then I will not write it, right? It's like one then. So positive or negative, finitely many primes. Okay, so do you want to take a guess what this RP is? It's obvious. Your obvious answer is correct. Why don't you tell me? So what I'm doing is, you have a fractional ideal which is global of A, and then I'm taking product with this local thing, and then I'm saying that it is PV power RP, where I'm saying that you can guess what RP is.
1.
Why do you say 1? Then that means every AAV is prime ideal. No, that can't be true. Take an example. So an example would be okay. So maybe you haven't done enough example, or I haven't done enough example. So think about it later. Take an example. Take Z. Take a number in everything as principal. Take an integer. Take 2. So question is, what is 2 times ZP? So 2 times ZP will be just the ideal generated by 2, right? So that is just 2. So there it is 1. Now take 4. What is 4 times ZP? It's ideal generated by 4 in ZP. But what is it? It is the ideal generated by 2 square, no? So what I want to say is, it does, whatever is the power coming here, it is exactly that power. So where A you can write as P power RP, etc. This is in A, in capital A, and the same RP will come. So this is a small check. You can easily check this. Conversely, any fractional ideal of AV is of the form PV power R, and PV power R intersection A is P power R. Basically, all that I'm saying is the indices are fully determined. The ramification, the indices are fully determined by the global ideal. What is happening locally is purely determined at the global level. Okay. So, so the only point is, these are easy things to check. I'm just stating it to show that ramification behaves well with completion, because now so where is ramification coming here? Here there's no ramification. So the point is, if you have E over K and A and B over A, and if you take an ideal and write it as a product, right? PB will be a product where the ramification indices come, and that after localization from this observation, it's exactly the same ramification index that will come for a given prime P. Of course, when you localize, there's only one prime, and yeah. So the point of this is, if see A may have, see, suppose A is A1 times, suppose A is P1 times P2. Okay, suppose A is P1 times P2, and A1, suppose A1 is P1 squared times P2. Then if V corresponds to P1, what one is saying is this product is just P1 power P1 square. If A had P1 square, then this is P1 square, and the other part disappears. If A had P2, but the valuation is with respect to P1, then in this product P2 will not come. That part will become like unit. Okay. So ramification is easier to study over local fields because there's only one prime above, and that ramification index can be understood from the global ramification index. So both these properties behave well, and this has the following consequence. So this is why different is important. Different is important because in order to study ramification, we can conclude a lot of things, not everything, but a lot, if you know how to compute the difference. So you have A Dedekind, K quotient field, E is a finite separable extension, B is the integral closure, all these things. And let's take this result. Assume that A by P is perfect for any prime P. Perfect meaning every extension, every finite extension is separable. We have always assumed this actually. So for all the primes, the quotient is perfect. And let capital P be a prime of B lying above P, and let E be the ramification index. Then E be the ramification index. Then the first claim is, so what is different? Different is an ideal of B, right? And we are saying that, so different is an ideal of B. You can, it's a Dedekind domain, so everything can be written as a finite product of prime ideals. So the different ideal will have a prime factorization. It's an ideal of B, so it will have a factorization involving prime ideals of B, and you can ask how many times this prime ideal P is coming. And if E is the ramification index of P, so if you take a prime P, then it lies over one prime, right? That is P intersection A, and that is small p. And if there is this ramification index, then we are saying that P comes at least E minus 1 times. So this is how ramification index is related to the different. You take the different, suppose you have a method of computing the different, and if you can compute the different and if you can factorize it, then the power of P, the ramification index of P, if the ramification index of P is E, then the power of P coming in this factorization of the different is at least E minus 1. That's the first result. And if the ramification is not tame, can you recall what is not tame? When we define ramified, we also define tamely ramified. Yeah?
So it's about the ramification index is not a power of, or is a power of P, which was
That was
different from
wild.
that.
Power of P or not
Yeah,
power?
it is not. It is not co-prime from P. I think that
Correct,
is not.
correct, correct.
Yeah.
So the point is, if P does not divide E, then we say tame. If P does not divide E, then we say tame. So not tame meaning P divides E. So if the ramification is not tame, okay, Lang calls it strongly ramified. Maybe we called it wildly ramified. So if the ramification is not tame, then P power E divides the difference. Then the value, the order of different at the prime P is at least E, if it's not tame. Okay, these are important observations. And therefore, if P is tamely ramified over P, then E minus 1 is the exact power of P in dB by A. That's clear, no? Because always P power E minus 1 will divide. Always P power E minus 1 will divide. If it's not tame, then one more thing, at least one more P will divide. P power E will divide. Therefore, if it is tame, then the exact order, exact power which divides is E minus 1. Okay. And what happens if P is unramified? Then P does not divide the difference. If P is unramified, then it does not divide the difference. So this is useful, no? So if we have a way of computing difference, then do you agree that ramification is easy to study? For example, whether something is unramified or not, it's clear now, no? Because suppose you know, I mean, we haven't shown how to compute the different, but suppose you have a method of computing different in a particular situation. Then you compute the different and suppose you know how to factorize it. We have methods of factorizing an ideal, right? Explicit factorization we have seen. And yeah, and suppose you can factorize the different, then if a prime is not appearing in that different, then what is the conclusion? Factorize the different, and so it will have only finitely many factors, right? Unique factorization meaning anything can be written as a finite product of primes. So finitely many primes will appear in the factorization of the different. Rest of the primes don't appear. So what is the conclusion? The primes that do not appear, they are all unramified. Unramified where? Unramified over the corresponding prime downstairs. So if you have capital P, you take capital P intersection A. So the conclusion is, so if this theorem is proved, which we are going to do in the next slide, if this theorem is proved, then in particular you can conclude that if you have A and B containing A, there are only finitely many prime ideals of A which will ramify. So if you take Z and Q root 2 and I think the ring of integers is Z bracket root 2, you can ask which primes will ramify. And they will be only finitely many and you can compute the different and see what goes into the different. So very few primes will ramify. Okay. So ramification is much easier by studying the different. So This is also due to Dedekind. And note that it follows that there are only finitely many primes P of A that ramify in B. Is it clear? This statement is clear to everybody. It's an important statement, and it just follows from this result if we approve this result. Is this clear? Because you look which primes come in the factorization of different. Only those are ramified. The rest are not ramified. And different is one ideal, no? So its factorization will have only finitely many primes. So only those finitely many primes are ramified primes. All others are unramified. Okay, so let's prove this result and then we will stop the lecture and then we can discuss a little bit. This is what we are going to prove. So it's an important result. Okay. So first observation is that we may assume that K is complete in order to prove this. This is a global result. K is quotient field of a Dedekind ring. There's nothing local about it. But I'm saying that you can assume that K is complete. Why is that? Because both ramification and difference will behave well with well with localization. So you could have assumed it's a DVR, and both these will behave well with completion. So you could have as well taken completion with respect to the prime, right? So that was the point of putting those two slides earlier, that different and ramification. Both these things behave well with respect to localization and with respect to completion. And therefore, if you want to compare these two without loss of generality, you can assume you are in the local situation. K is complete because both these properties behave well with completion. Okay, so we know by this result of where we applied Nakayama and some valuation in the last class, we proved that in the local situation, right? Whenever you have a DVR, and whenever you have a DVR and one prime lying above, we have shown that the ring of integers B is A bracket alpha for one alpha. And this can be applied in the local situation because you are in the it's also complete and it's a DVR and you have exactly one prime lying above. So that result is true, and therefore you have B equal to A bracket alpha for some alpha. This is always true because you are assuming it is complete. Okay. Now you recall we had a corollary last time that if B is of this particular form, right? We had this theorem where we wrote down this explicit dual basis for K alpha over K. You take the basis 1 alpha, alpha square, etc. And we had this dual basis in terms of the minimal polynomial of alpha. And it had an immediate corollary, which is that if B is of this form, A bracket alpha, then what do you know about B prime? The dual lattice B prime. This we did last time. Dual lattice B prime is generated by one element. And what is that element? 1 by F prime alpha. Okay, so B prime is 1 by F prime alpha B. Check your notes of last class, it's there. Okay, and therefore what can you say about the different? Different is the inverse of this, no? So what can you say about the different? Different is generated by F prime alpha. So if B is of the form A alpha, then the different is generated by F prime alpha. And this is good. So the crucial step was this completion. Without loss of generality, you have reached completion. And in the completion, in the complete situation, in the local situation, you know that this is true. And therefore, you have computed B prime. It is 1 by F prime alpha B. And therefore, different is the inverse of that fractional ideal. So this is generated by this. Now assume E over K is unramified. What do we need to show when E over K is unramified? The result is that P will not divide the different. And we are going to show that the different is trivial if E over K is unramified. So if E over K is unramified, then E is generated by one element alpha. And what is the property of alpha? We had characterized unramified extensions, totally ramified extensions, totally and tamely ramified extensions. All these characterizations we have done in chapter 2. So unramified extensions are such that the minimal polynomial of alpha, what is the property? Its reduction mod P will have no multiple roots. So in particular, it will be irreducible. So minimal polynomial f of alpha is such that its reduction mod P is irreducible. If this is the case, then what can you say about f prime alpha? F has the property, f anyway is a separable polynomial, it's a minimal polynomial. I mean, you are assuming E over K is separable. So f is separable, f has no repeated roots. But in addition, its reduction mod P also has no multiple roots. How do you know it has no multiple roots? Because we know that it is, yeah, if reduction mod P has now, how did we conclude it's irreducible? Because we were in the situation 1 prime lying above, and therefore something that we had done long back, we knew that reduction mod P will be the power of an irreducible polynomial. And because it has no multiple roots, that power has to be 1. It cannot be a genuine power, because then there will be multiple roots. Okay, so this we know, reduction mod P is irreducible. So now the question is, what can you say about f prime alpha? And the conclusion is, I am going to say that f prime alpha is a unit. Why? Because if f prime alpha is not a unit, then it is inside P. So reduction mod P, right? What we know is reduction mod P of f is irreducible. So if f prime alpha is not a unit, then its reduction mod P will be right. So if you take bar, so f bar prime, what can you say about f bar prime if f prime alpha is not a unit? If f prime alpha is not a unit, then f bar prime will be identically 0, right? So that will contradict the fact that the reduction mod P is irreducible. If you have a polynomial whose prime is vanishing, then there's a problem. So it's a small check. You conclude that f prime alpha is a unit. And if f prime alpha is a unit, then what is the conclusion? It is generated by a unit. Therefore, it is the unit ideal, meaning the full ring. And if it's a full ring, then of course there is no prime which divides. This is what we wanted to show. In the unramified situation, primes will not divide. By completion, we needed to check only for the local situation, and this is a proof. Okay, so what happens when is okay, no? Yeah, is there a question?
No, I said yes.
Okay, okay, fine, good, yeah. So this is basically the idea. So most of the important part is, is done already here. Without loss of generality, that we could come here. That is what is simplifying this thing. Therefore, we could apply all the nice things that we had. We could apply. Okay. So in this case, we are done. Now, what is there to be done? Now we have to show that if E is the ramification index, and P power E minus 1 always divides. But now that in the unramified situation, different is trivial, and we also know transitivity of different. Therefore, any extension, if E over K is any extension, you know that it can be written as a totally ramified extension over an unramified extension, right? This we had seen. You can take the maximal unramified extension of K contained in E. Take all possible unramified extensions of K contained in E and take the composite term. That will be unramified, and that is the maximal unramified extension of K contained inside E, and E over that extension is totally ramified. So you can put this unramified extensions in between so that that other extension is totally ramified, And how is it different behaving in a tower of extensions? Different is transitive. So if you have E over F over K, then different of that times different of this is the different of the full extension. So, and different of this unramified part is trivial. So what that means is different of an extension is same as different of the totally ramified part. So without loss of generality, you can assume by transitivity of the different, without loss of generality, you can assume that E over K is totally ramified. Now, do you remember the keyword totally ramified extensions? What was the characterization? That was also generated by a single element. What was the property? What was the keyword? There was no one name. Totally ramified extensions are generated by a root of
Eisenstein.
yeah, Eisenstein. So it's generated by root of an Eisenstein polynomial. So B is of the form A generated by one element, let's call it pi E, where pi E satisfies an Eisenstein polynomial, where this ramification index E is same as the degree of E over K. It's totally ramified. It's Eisenstein. So P divides all these things, meaning AI belongs to P, and this is order one element. This does not belong to P square. So valuation of pi is 1. This we knew. And from this you can conclude that, so this is F, right? F is the minimal polynomial. This is F. And what can you say about F prime at pi E? That is E pi E, E minus 1. And then the next term will be E minus 1 times AN minus 1 times pi E power E minus 2. But we don't know about the valuation of this. We know that this is bigger than E because it belongs to P. P upstairs will be capital P times power E. So this has valuation at least E. So all the other terms belong to capital P power E. So mod capital P power E F prime is this. And therefore you are done, right? Because you know that the different is generated by F prime alpha. Different is generated by this. So the different has P power E minus 1 dividing it. Exactly P power E minus 1, E will be a unit. But if P divides E, then this pi E power E minus 1 becomes something bigger than E because E will also contribute. So everything is done from this congruence relation. This should be congruent. Clear? Is the last step okay? So you get the Eisenstein polynomial and you take the formal derivative. You get E times pi E power E minus 1. So if E doesn't have a P in it, then the exact valuation is E minus 1. If E has a P in it, you don't know how many times E has a P in it. Depending on how many times it's there, it will contribute extra. So in the widely ramified things, you only know that P power E divides. It could be a higher power. In the tamely ramified thing, the power of P that divides different is exactly E minus 1. Okay, so this is very important. So I think we should do some examples and all that we will discuss. So let me stop the lecture part and we will discuss how we will do examples in some of these other classes where you should do, not me. So we will discuss how we will go about it. So lecture part is over. There are some typos. Let's correct that. So let me stop the recording. Let me stop the recording.